April 19th, 1941, Fort Benning, Georgia. A brilliant spring morning, temperature 68 degrees, visibility unlimited, winds calm at 3 knots from the southwest. 4 Boeing B-17 Flying Fortress bombers circled at 12,000 feet above a simulated battleship target painted on the bombing range below. The target measured 600 feet long by 105 feet wide, roughly the dimensions of a Japanese Congo-class battleship. Inside the lead aircraft, the bombardier hunched over a device that weighed 50 pounds and contained 2,000 precisely machined parts. His hands moved across control wheels, making minute adjustments. Through the eyepiece of the Norden Mark 15 bombsight, crosshairs tracked the target automatically, compensating for wind drift, aircraft speed, and altitude. The analog computer inside the device continuously recalculated the bomb's trajectory, adjusting for variables that would have required lengthy manual calculations with any previous bombsight. At the precise moment computed by the machine, bombs released. Then the second aircraft, then the third, then the fourth. 12 bombs of various sizes fell toward the target from 12,000 feet. Military observers on the ground watched through binoculars, notebooks ready. 10 bombs struck the simulated battleship. 2 missed by narrow margins. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. 5 days later, the acting chief of the Bureau of Aeronautics sent an enthusiastic letter to the Secretary of the Navy. His words carried absolute conviction and would shape American strategic bombing doctrine for the next 4 years. The Norden Bombsight is considered to be the principal single factor of superiority which the air forces of this country possess over those of potential enemy countries. The demonstration seemed to validate everything military planners believed about precision bombing. Small formations of heavy bombers, flying at altitudes beyond the effective range of anti-aircraft fire, could destroy specific military targets with surgical precision. Ships, factories, railroad yards, power plants, bridge abutments. The technology existed to transform aerial bombardment from random destruction into calculated strikes that would cripple enemy war-making capacity while minimizing civilian casualties. 7 months later, on December 7, 1941, Japanese aircraft attacked Pearl Harbor. The United States entered a global war that its military leadership believed it would win through technological superiority. The Norden Bombsight represented the pinnacle of that confidence, a mechanical marvel so sophisticated that bombardiers swore oaths to protect its secrets with their lives, so revolutionary that armed guards accompanied each device from storage vaults to aircraft, so advanced that the government spent more than $1 billion developing and producing it. The promise was extraordinary. Company President Theodore Bart proclaimed that his firm did not regard a 15-foot square as being a very difficult target to hit from an altitude of 30,000 feet. Promotional materials claimed bombardiers could drop bombs into Pickle barrels from 20,000 feet. Military planners built an entire strategic doctrine on these claims, committing tens of thousands of lives to bombing campaigns that depended on precision the Norden supposedly guaranteed. Within 2 years, combat would reveal a different truth. The 75-foot accuracy achieved at Fort Benning would become 1,200 feet or worse over defended targets in Europe and Asia. The secret weapon would prove neither as secret nor as effective as believed. The technological confidence that defined American military planning would collide with the brutal realities of combat at 25,000 feet, in sub-zero temperatures under anti-aircraft fire and fighter attack. The transformation from confidence to disillusionment would reshape not just bombing tactics, but American understanding of what technology could achieve in warfare. The story of that transformation begins not at Fort Benning but 2 decades earlier, in the cramped apartment of a difficult, brilliant engineer who believed he could solve the unsolvable problem of precision bombing from high altitude. Part 2. Building the World. The context. The problem of dropping bombs accurately from aircraft had plagued military planners since the first pilots attempted it during World War I. The mathematics were deceptively simple in theory, devastatingly complex in practice. A bomb released from a moving aircraft did not fall straight down. It maintained the forward velocity of the aircraft while gravity pulled it downward. Wind affected the trajectory. Air density changed with altitude and temperature. The bomb's shape and weight influenced how it fell. A pilot flying at 10,000 feet at 150 miles per hour needed to release the bomb thousands of feet before reaching the target, but calculating that exact point required knowing precise airspeed, exact altitude, accurate wind speed and direction, and the ballistic properties of the specific bomb being dropped. Early bomb sights were crude. Some consisted of nothing more than notches carved into a wooden crossbar or lines drawn on a structural spar. The pilot estimated the release point based on experience and intuition. Accuracy was abysmal. During World War I, the British developed the course-setting bomb sight, which incorporated a slide rule calculator to help estimate wind effects. The United States Army adopted simpler designs like the Estopi D series, which automatically leveled the sight during use. These systems improved accuracy marginally but still required lengthy manual calculations before each bomb run. By the early 1920s, military theorists had begun conceptualizing strategic bombing as a potentially decisive weapon. The idea was revolutionary. Rather than engaging enemy armies directly, air forces could strike at the industrial heart of enemy nations, destroying factories, power plants, transportation networks, and production facilities. Strategic bombing promised to win wars by eliminating the enemy's capacity to fight, bypassing the horrific trench warfare that had defined World War I on the Western Front. The doctrine required precision. Random bombing of cities served no strategic purpose and violated emerging international norms about protecting civilians. Effective strategic bombing meant hitting specific targets: ball-bearing factories in Schweinfurt, synthetic oil refineries in Leuna, aircraft production facilities in Regensburg. Success demanded bomb sights far more sophisticated than anything existing technology offered. The United States Navy Bureau of Ordnance recognized this requirement in 1920. They needed a bomb sight capable of precision attacks against moving warships from high altitude. Existing dive bombers and torpedo bombers were effective but vulnerable, forced to attack from low altitude where anti-aircraft fire and defensive fighters could destroy them easily. High-altitude horizontal bombing offered safety but lacked accuracy. The Navy wanted both safety and precision. They contracted with Carl Lucas Norden, a Dutch immigrant with a reputation for brilliant gyroscope design. Norden had worked for Elmer Sperry developing ship stabilization systems before leaving to establish his own consulting practice. He was 40 years old, possessed of extraordinary engineering talent and an equally extraordinary difficult personality. Navy officers called him Old Man Dynamite. Colleagues described him as impatient, domineering, abrasive, a perfectionist who drove himself relentlessly and expected the same from everyone around him. Norden approached the bomb sight problem with characteristic intensity. Existing designs relied on the bombardier estimating variables and making calculations. Norden proposed automating those calculations using gyroscopically stabilized platforms and mechanical analog computers. The gyroscopes would keep the optical system stable despite aircraft movement. The analog computer would continuously recalculate the bomb's trajectory as flight conditions changed. An autopilot connection would allow the bomb sight to fly the aircraft during the final bomb run, compensating automatically for wind drift. Development consumed most of the 1920s. Norden worked from his partner Theodore Barth's apartment in New York City, borrowing equipment from aircraft manufacturers, hand-building prototypes. Testing at the Naval Proving Ground in Dahlgren, Virginia, revealed constant problems. The early designs were too complex, requiring both hands, both feet, and the teeth to operate, as one Navy bombardier complained. Open cockpits made fine adjustments nearly impossible. Vibration affected the gyroscopes. The pilot direction indicator malfunctioned. Leveling the platform required lengthy procedures that consumed valuable time during bomb runs. Part 3. Building the World. The Ideology. By 1931, Norden had solved most of these problems. The Mark 15 bomb sight incorporated synchronous measurement of ground speed, eliminating manual calculations entirely. The device tracked targets automatically through a telescopic sight, while the analog computer continuously calculated trajectories. At the precise release point, it dropped bombs automatically. More importantly, it connected directly to the aircraft's autopilot, allowing it to fly the airplane during the critical final approach, making constant tiny corrections that human pilots could not match. Testing demonstrated astonishing accuracy. Circular error probable, the radius of a circle within which 50% of bombs would fall, measured 75 feet from 21,000 feet altitude. This was unprecedented performance, revolutionary for the era. Navy officers were ecstatic. The United States Army Air Corps, observing these results, immediately wanted the Norden for their strategic bombing doctrine. American military culture in the 1930s embraced technological solutions with near-religious fervor. The nation's industrial capacity was the world's largest. American engineering had built transcontinental railroads, massive hydroelectric dams, soaring skyscrapers, and the world's most productive factories. Military planners believed this same technological and industrial superiority would prove decisive in future wars. The Norden Bombsight seemed to embody these beliefs perfectly. The strategic doctrine built around the Norden differed fundamentally from European approaches. The British Royal Air Force, learning from early bombing attempts, concluded that precision attacks were impractical. They adopted area bombing, saturation attacks on entire cities conducted at night to reduce losses to anti-aircraft fire and fighters. The approach prioritized mass destruction over surgical strikes. It accepted that civilian casualties would be enormous. American planners rejected this doctrine as both inefficient and morally questionable. They believed precision technology made area bombing unnecessary. The Norden would enable small formations of heavy bombers to destroy specific industrial targets from high altitude, eliminating enemy war-making capacity while avoiding the mass slaughter of civilians. The approach appealed to American sensibilities about warfare, the belief that superior technology and industrial capacity could achieve military objectives more humanely than crude force. This ideology was not merely propaganda, though it served propaganda purposes. Military planners genuinely believed precision bombing would work. The Fort Benning demonstration provided evidence. The Norden's performance in testing exceeded anything previous bomb sites had achieved. The B-17 Flying Fortress provided the platform to deliver this capability deep into enemy territory. The combination seemed unbeatable. Security surrounding the Norden reflected both its importance to strategic doctrine and the need to maintain morale. The device was classified top secret. Bombardiers in training swore formal oaths to protect the bomb site's secrets with their lives if necessary, to destroy it rather than allow capture by enemy forces. The oath ceremony was deliberately solemn, emphasizing the bombardiers' crucial role in American military superiority. When not installed in aircraft, the upper portion of the bomb site, called the sight head or nicknamed the football by bombardiers, was removed and stored in vaults under armed guard. Before each mission, jeeps carrying ordnance technicians escorted by armed soldiers would deliver sight heads to waiting bombers. Bombardiers installed the devices but could not remove protective covers until airborne. The ritual reinforced the Norden's status as America's secret weapon, the technological edge that would enable victory. Propaganda materials emphasized the bomb site's precision without revealing technical details. Newspaper articles repeated claims that bombardiers could hit Pickle barrels from 20,000 feet. Newsreels showed bombs striking targets in training exercises. The message was clear to both American citizens and enemy nations. American technology provided capabilities no other nation possessed. Strategic bombing would destroy enemy war-making capacity with scientific precision, avoiding the indiscriminate destruction of total war. The ideology extended beyond military circles. American industrial leaders saw the Norden program as validation of mass production capabilities. The device contained 2,000 precision parts, each manufactured to tolerances finer than expensive watches. Producing tens of thousands of these complex machines demonstrated American industrial sophistication. The program cost exceeded $1 billion, roughly half the cost of developing atomic weapons, making it one of the most expensive military projects of the war. Such investment seemed justified given the Norden's promised capabilities. By December of 1941, when the United States entered World War II, The ideology of precision bombing, undergirded by Norden technology, was firmly established. Bombardiers trained extensively on the device, learning to operate what was essentially an analog computer under combat conditions. Factories geared up for mass production. Strategic planners designed bombing campaigns around the assumption that small formations could destroy specific targets with acceptable accuracy. The foundation of belief was complete. Technology would enable precision, precision would enable strategic bombing. Strategic bombing would win the war efficiently while minimizing civilian casualties. The Norden Bombsight made all of this possible. Within months, combat would begin testing these assumptions against the brutal realities of aerial warfare over defended territory. The Norden Mark 15 bombsight that entered mass production in 1942 consisted of two main assemblies. The stabilizer, which remained permanently installed in the aircraft, contained a directional gyroscope and connected to both the autopilot system and the bomb release mechanisms. The sight head, the famous football that bombardiers guarded so carefully, contained the telescopic sight, the analog computer, and a second gyroscope for additional stabilization. Together, these assemblies weighed approximately 50 pounds and cost $8,800 per unit. The stabilized bombing approach equipment, which provided the autopilot connection, added another $4,200, bringing the total cost to $13,000 per complete system in $1,942. Inside the sight head, two direct current-powered gyroscopes spun at 7,800 revolutions per minute. These provided the stable platform necessary for accurate sighting despite aircraft movement. The gyroscopes had to maintain perfect balance. Even slight imperfections in the bearings could cause drift, destroying accuracy. Ball bearings were manufactured to tolerances measured in 10,000ths of an inch, finer than those in expensive Swiss watches. The Norden Company established its own bearing manufacturing facility, the Baden Company, because existing suppliers could not meet the quality requirements. Skilled craftsmen, most of them German or Italian immigrants, hand-assembled each bombsight before the war. Between 1932 and 1938, production averaged only 121 units per year. The telescopic sight provided 20-power magnification, allowing bombardiers to identify factory complexes and railroad yards from high altitude, though not the individual buildings within them, and certainly not objects as small as pickle barrels. The analog computer consisted of mechanical gears, cams, and linkages that continuously solved differential equations relating aircraft speed, altitude, wind velocity, and bomb ballistics. The bombardier input known variables: airspeed from the pilot, altitude from instruments, and estimated wind from weather briefings. The computer then calculated the continuously changing angle to the target as the aircraft approached. Training bombardiers to operate this complex device required 3 months of intensive instruction. The curriculum at bombardier schools, like the one at Childress Army Airfield in Texas, began with basic principles of ballistics and navigation. Students learned to read instruments, calculate wind drift, and understand how altitude and temperature affected bomb trajectories. They practiced on ground-based trainers before progressing to actual flights. The Norden's operation demanded precise technique. Before each mission, the bombardier had to right the stabilization platform, a time-consuming process involving spirit levels viewed through a glass window on the stabilizer's front. The platform drifted slowly over time and had to be manually adjusted to perfectly vertical orientation. This process alone could take 15 minutes in a cold, cramped aircraft. Once righted, the bombardier would dial in initial parameters: airspeed, altitude, and heading. The sight head would be clutched out, allowing free movement to search for the target. Later model Nordens included a reflector sight to aid this search phase. When the target was located, the bombardier clutched the computer back in, and the device began automatically tracking. 2 control wheels allowed fine adjustments. The rate wheel adjusted for range rate, how quickly the aircraft approached the target. The trail wheel adjusted for crosswind drift. The bombardier made constant tiny corrections based on visual observation of how the crosshairs tracked across the target. The process required intense concentration while looking through an eyepiece, hands on control wheels, maintaining position in a freezing, unpressurized aircraft at 25,000 feet. The autopilot connection, called the Stabilized Bombing Approach equipment, represented a crucial innovation. During the bomb run, the bombardiers' adjustments to the Norden's controls automatically commanded the aircraft's autopilot. The pilot took his hands off the controls. The bombsight flew the airplane, making constant corrections far more precisely than human pilots could manage. This automated control lasted for the final 3 to 5 minutes before bomb release, the most critical and dangerous phase of the mission when the aircraft had to maintain steady course and altitude over the target. Bombardiers practiced these procedures hundreds of times in training. They dropped practice bombs on ranges in the American Southwest, where weather was predictable, and enemy fighters and anti-aircraft fire were non-existent. Under these ideal conditions, accuracy was impressive. Training graduates could consistently place bombs within 300 feet of targets from 20,000 feet. The circular error probable during training averaged approximately 250 feet, far better than any previous bombsight system achieved. The training emphasized the bombardier's crucial role. He controlled the airplane during the bomb run. The mission's success depended entirely on his skill with the Norden. Instructors reinforced the psychological importance of precision. American strategic doctrine required hitting specific targets. Unlike British area bombing, which accepted massive civilian casualties, American precision bombing would destroy military and industrial facilities while sparing civilian populations. The Norden made this moral approach possible. Bombardiers carried this belief into combat, confident their technology and training would enable surgical strikes. Part 5. The Deep Dive, Production and Reality. The conversion from handcrafted prototypes to mass production created immediate problems. The Norden's complexity defied conventional manufacturing processes. Each unit contained 2,000 parts requiring tolerances far beyond normal industrial standards. Gears had to mesh perfectly. Gyroscope bearings could not vary by even thousandths of an inch. Optical elements needed precise alignment. Any defect in any component could render the entire bombsight inaccurate or non-functional. Before the war, skilled craftsmen assembled each bombsight individually, adjusting and fitting parts by hand. This artisanal approach became impossible once the Army Air Forces demanded thousands of units. Carl L. Norden, Incorporated had to transform from a small engineering firm into a major manufacturer. The company established facilities in New York City and licensed production to Victor Adding Machine Company and Remington Rand. By 1943, 6 factories were producing Norden Bombsights. Total wartime production reached approximately 90,000 units across all services. Quality control became a critical challenge. The devices required constant calibration. Rough handling during transportation or installation could damage sensitive components. Hard landings could flat-spot gyroscope bearings, necessitating complete overhaul. Temperature extremes at bombing altitude affected lubricants and caused metal components to contract. Undoubtedly, many missions were flown with bombsights operating out of specification. Their accuracy degraded by mechanical problems bombardiers could not detect or correct. The Army Air Forces purchased electrically heated blankets for the bombsights to prevent lubricating oils from congealing at altitude and to stop optical elements from fogging. Even with these measures, equipment failures were common. Carbon dust from direct current motor brushes spread into sensitive bearings, causing additional wear and drift. Vibration from the aircraft's engines and from anti-aircraft explosions affected gyroscope stability. Electrical surges from battle damage could destroy delicate circuits. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Maintenance personnel struggled to keep the devices functional. Each bombardment group had specialists trained in Norden maintenance and calibration. These technicians worked under enormous pressure. The maintenance manual's introduction stated explicitly, "Upon the shoulders of the bombsight, maintenance personnel rests the responsibility of accurate calibration and maintenance, and to that extent the success or failure of a bombing mission. You cannot and must not make any attempt to shift that responsibility." The reality of combat operations made this responsibility nearly impossible to fulfill. Bomber groups flew missions continuously, sometimes daily when weather permitted. Maintenance crews had limited time between missions to inspect, calibrate, and repair bomb sites. Parts were often in short supply. Replacement gyroscopes, bearings, and optical elements had to be manufactured to exacting specifications and then shipped to bases in England, Italy, and the Pacific. The logistics chain frequently failed under the strain of global war. Combat conditions degraded accuracy in ways testing had never anticipated. At training ranges in Texas and New Mexico, bombardiers operated in clear weather with unlimited visibility. Over Europe, cloud cover was constant. The 8th Air Force, operating from bases in England, frequently encountered solid overcast that made visual bombing impossible. Missions were scrubbed or diverted to alternate targets. When clouds parted enough to permit bombing, windows of opportunity lasted only minutes. Bombardiers had to locate targets quickly, often with limited visibility and smoke from previous bombing obscuring landmarks. Anti-aircraft fire created additional problems. German flak batteries defending industrial targets fired thousands of rounds during each raid. The 88mm guns were accurate up to 26,000 feet. Exploding shells created turbulence that buffeted aircraft violently. Bombardiers attempting to make fine adjustments to the Norden found their aircraft suddenly dropping or climbing hundreds of feet, rolling left or right, as shock waves from nearby explosions hit them. Maintaining the steady, level flight path necessary for accurate bombing became nearly impossible. Fighter attacks forced bombers into tight defensive formations. The B-17 seconds and B-24 seconds flew wingtip to wingtip, sometimes with only feet of separation, to concentrate defensive machine gun fire and protect against attacking Messerschmitt and Focke-Wulf fighters. These close formations eliminated the independent maneuvering necessary for precision bombing. Individual bombardiers could not adjust their flight paths to compensate for wind drift or to line up perfectly on their assigned targets. They flew formation, maintaining position relative to other aircraft, regardless of where that positioned them relative to the target. Part 6. The Climax of Reality. Schweinfurt, August 17, 1943. The mission planners at 8th Air Force Headquarters in England had identified the target months earlier. Schweinfurt, a city in Bavaria, housed factories producing more than half of Germany's ball bearings. Every German aircraft, tank, artillery piece, and machine gun required precision bearings. Destroying these factories would cripple German war production across all categories. Intelligence estimates suggested that eliminating Schweinfurt's output would reduce German fighter production by 66% within months. The raid would demonstrate American daylight precision bombing at its most ambitious. 230 Boeing B-17 Flying Fortresses would attack Schweinfurt, while another 146 attacked Messerschmitt factories in Regensburg. The Regensburg force would continue to North Africa after bombing, a shuttle mission designed to confuse German defenses. Both forces would fly without fighter escort for most of the mission. American P-47 Thunderbolt fighters had insufficient range to accompany the bombers to targets deep in Germany. The Schweinfurt force took off in the early afternoon. Weather over England was poor, delaying departure and eliminating any surprise factor. German radar detected the formations immediately. Luftwaffe fighter controllers vectored interceptors toward the bomber stream. Messerschmitt Bf-109 and Focke-Wulf FW-190 fighters began attacking as soon as American escorts turned back. The attacks continued for more than 2 hours. German fighters made head-on passes, firing cannons and machine guns into the tight bomber formations. They dropped aerial bombs into the formations from above. They fired rockets from beyond defensive machine gun range. The bomber crews fought back desperately, but losses mounted. B-17 seconds fell out of formation, trailing smoke and flame. Parachutes blossomed as crews abandoned aircraft. Some bombers exploded in mid-air when fighters hit fuel tanks or bomb loads. First Lieutenant Robert Abb, bombardier aboard the B-17F Pretty Baby, hunched over his Norden M7 bombsight as his aircraft approached Schweinfurt. Through his intercom, he called instructions to the pilot while monitoring fighter attacks and flak. Target ahead. About 15 degrees left, maybe 6 miles. Watch that formation, stay in there tight. Lead group is going in now. Top turret, fighter at 11 o'clock our level. They look like 4 190s. Here he comes. Nice shooting, think you got him. Approaching initial point, give me a level, start the camera. The coordination required between bombardier, pilot and defensive gunners was extraordinary. Ab had to concentrate on the Norden's controls, while aircraft around him were being shot down, while fighters attacked from multiple directions, while anti-aircraft shells exploded nearby. The psychological strain was immense. Bombardiers trained in peaceful southwestern skies now operated their sophisticated equipment while watching friends die, while enemy shells burst close enough to hear fragments hitting the aircraft, while the knowledge that any moment might bring the cannon shell or rocket that would kill them. Over Schweinfurt, German anti-aircraft defences opened up with full intensity. The factories were heavily defended by flak batteries positioned around the city's perimeter. 88mm shells created a curtain of explosions through which the bombers had to fly. Pilots held steady courses during the bomb run, allowing the Norden Bombsights to control the aircraft. This steady, straight, level flight made them perfect targets for flak gunners who had practiced these scenarios hundreds of times. The bombs fell. Thousands of 500-pound general-purpose bombs and incendiaries dropped toward the factory complexes below. Bombardiers watched through their eyepieces as the bombs fell away, hoping to see strikes on target. Smoke from earlier groups obscured the results. The bombers turned away from the target, still under heavy fighter attack, beginning the long flight back to England. 60 B-17 seconds did not return. 600 men were dead, captured, or missing. Another 17 aircraft were damaged beyond repair and scrapped after landing. More than 100 aircraft sustained battle damage. The casualty rate exceeded 25%, far beyond sustainable losses for continued operations. The Regensburg raid lost 24 aircraft, bringing the total losses for the day to 84 heavy bombers. Post-mission reconnaissance revealed the results. The bombing had damaged the Schweinfurt factories but not destroyed them. Production declined but did not cease. Within months, German industrial planners had dispersed ball-bearing production to multiple smaller facilities and increased imports from neutral Sweden. The strategic effect was far less than anticipated. The Norden Bombsights, operating under combat conditions, had not delivered the precision that testing and training had promised. The psychological impact on bomber crews was profound. Men who had trained believing they possessed technological superiority faced the reality that neither their equipment nor their courage could guarantee survival or success against determined, well-prepared defenders. The Schweinfurt raid forced American military leadership to confront uncomfortable truths about daylight precision bombing. Within weeks of the August 17th mission, statistical analysis confirmed what bomber crews already knew. The Norden Bombsight, operating under combat conditions, achieved accuracy far below testing predictions. Studies of bombing photographs and damage assessment reports revealed that only 31.8% of 8th Air Force bombs fell within 1,000 feet of their aiming points, from an average altitude of 21,000 feet. The 15th Air Force, operating from bases in Italy, averaged 30.78% from 20,500 feet. Against Japanese targets, the 20th Air Force averaged 31% from 16,500 feet. These figures represented the performance of the most experienced bombardiers using the most sophisticated bomb sight in the world under the best possible combat conditions. In poor weather, with heavy cloud cover, the accuracy degraded further. In the presence of intense anti-aircraft fire and fighter attacks, it degraded even more. The 75-foot circular error probable achieved at Fort Benning in April of 1941 had become 1,200 feet or worse in actual combat. Some bombing errors were measured in miles rather than feet. The strategic implications were severe. Precision attacks on specific factories or transportation nodes, the foundation of American bombing doctrine, were not achieving their intended effects. The Schweinfurt ball-bearing factories, despite repeated raids, continued operating at reduced capacity. German industrial planners dispersed production to smaller facilities scattered across occupied Europe, They increased imports from neutral Sweden. They prioritized military production over civilian goods, accepting declining living standards to maintain war material output. The bombing had economic effects, but did not produce the crippling blow that doctrine predicted. American commanders faced a difficult choice. They could acknowledge the limitations of precision bombing and adopt British-style area attacks, accepting massive civilian casualties. They could continue precision attacks despite their demonstrated ineffectiveness, accepting unsustainable bomber losses. Or they could develop new tactics that preserved the fiction of precision while effectively implementing area bombardment. They chose the third option. The lead bomber procedure emerged as the primary tactical adaptation. Rather than having each bombardier in a formation independently aim and release bombs using his Norden sight, formations designated lead bombardiers in specially equipped aircraft. These lead aircraft carried the most experienced bombardiers and the best-maintained Norden sights. All other bombardiers in the formation simply watched the lead aircraft and toggled their bombs when they saw the lead bomber's bombs release. This toggling technique meant that dozens or hundreds of aircraft dropped their bombs simultaneously based on one bombardier's aim. The tactical shift improved formation, cohesion, and simplified operations, but eliminated individual precision entirely. If the lead bombardier's aim was slightly off, every bomb in the formation missed by that same margin. The technique effectively transformed precision bombing into area bombing while maintaining the appearance of targeted attacks. Official reports still claimed precision raids on specific facilities. The reality was that entire industrial districts, including surrounding residential areas, were being saturated with high explosives and incendiaries. Bomb loads shifted toward incendiaries designed to start fires rather than high explosives intended to destroy specific structures. Fire created its own targeting system. Incendiaries falling across a wide area would start multiple fires that, under the right conditions, could merge into firestorms, generating their own wind patterns and consuming everything, within vast areas. The firebombing of Hamburg, in July of 1943, conducted primarily by the British Royal Air Force, demonstrated the technique's devastating effectiveness. 42,600 civilians died in firestorms that reached temperatures exceeding 1,000 degrees Fahrenheit. American forces gradually adopted similar tactics while maintaining the language of precision bombing. Official statements continued emphasizing targeted attacks on military and industrial facilities. Mission reports listed specific factories as targets. Bombardiers continued using their Norden sights to aim at designated points. But the reality was that entire cities were being destroyed, not through deliberate policy of area bombing, but through the accumulated effect of precision attacks that were not actually precise. The psychological burden on bomber crews intensified. They had trained believing they would conduct surgical strikes on military targets. They had been told their technology enabled precision that would spare civilians. They discovered that neither their equipment nor the tactical situation allowed such discrimination. They participated in campaigns that killed hundreds of thousands of civilians. The Norden Bombsight, which was supposed to make this unnecessary, instead provided moral cover for devastating attacks that differed little from the British area bombing American doctrine had originally rejected. Part 8. Aftermath, the final missions. By 1945, the gap between Norden mythology and combat reality had become impossible to ignore. The strategic bombing campaign over Europe had destroyed German industrial capacity, but through mass attacks involving hundreds or thousands of bombers rather than the small precision formations originally envisioned. The casualties were staggering on all sides. The 8th Air Force alone lost more than 4,700 heavy bombers in combat. Approximately 47,000 American airmen died in the European theatre. German civilian deaths from bombing exceeded 300,000, possibly far more, with exact figures impossible to determine due to the destruction of records and the displacement of populations. Against Japan, the transformation from precision to area bombing became explicit. In March of 1945, Major General Curtis LeMay, commanding the 20th Air Force's B-29 Superfortress operations, ordered a fundamental tactical change. Rather than high-altitude precision attacks using Norden bombsights, His bombers would attack Japanese cities at night from low altitude, 5,000 to 8,000 feet, carrying maximum loads of incendiary bombs. The Norden played minimal role in these attacks. Precision was unnecessary and undesired. The goal was to create firestorms that would consume entire urban areas. The raid on Tokyo, the night of March 9th and 10th, demonstrated the new doctrine's horrific effectiveness. More than 300 B-29 seconds dropped approximately 1,665 tons of incendiaries on residential districts. The resulting firestorm killed approximately 100,000 people, possibly as many as 125,000. 16 square miles of the city burned completely. The heat was so intense that canals boiled. People caught in the open were incinerated instantly. Those who sought shelter in concrete buildings suffocated as the fires consumed all oxygen. The death toll exceeded that of either atomic bomb attack that would follow 5 months later. The Norden Bombsight, which had promised to make such mass slaughter unnecessary through precision technology, was largely irrelevant to these attacks. Bombardiers still sat at their stations, still looked through their sights, but they were aiming at entire neighborhoods rather than specific facilities. The sophisticated analog computer, the gyroscopically stabilized platform, the 2,000 precision parts manufactured to tolerances finer than expensive watches, none of this mattered when the target was an entire city and success was measured in square miles consumed by fire. On August 6, 1945, the B-29 Enola Gay departed Tinian Island carrying the atomic bomb Little Boy. Bombardier Thomas Ferriby used a modified Norden Bombsight to aim at the Aioi Bridge in Hiroshima. The bomb detonated approximately 800 yards from the intended aiming point over the Shima Surgical Clinic. The error of 800 yards, which would have represented complete failure for a conventional bomb, was utterly irrelevant. The atomic blast destroyed everything within approximately 1 mile of the detonation point and caused severe damage across a much wider area. Approximately 70,000 people died immediately. Tens of thousands more would die from radiation effects in subsequent months and years. 3 days later, the B-29 Boxcar dropped the atomic bomb Fat Man on Nagasaki. Cloud cover obscured the primary target. The bombardier aimed at a visual target of opportunity using radar assistance. The bomb detonated approximately 2 miles from the intended aiming point. Again, the error was meaningless given the weapon's destructive power. Approximately 40,000 people died immediately, with tens of thousands more succumbing to radiation effects later. The atomic bomb missions represented the ultimate irony of the Norden story. The most expensive bomb site in history, developed at enormous cost and protected with unprecedented secrecy, delivered the most expensive bombs in history to end the war. The Norden's actual accuracy was nearly irrelevant. Nuclear weapons rendered precision bombing obsolete. The devastation they caused exceeded anything possible with conventional bombs regardless of accuracy. The entire strategic bombing doctrine built around the Norden, the careful calculations of which, factories to target and in what sequence, became instantly archaic. Japan surrendered on August 15, 1945. The war that American planners believed they would win through precision technology had been won partly through the most imprecise weapon imaginable, atomic bombs that destroyed everything within miles of their detonation points. The Norden Bombsight, which was supposed to enable surgical strikes, had instead provided moral and technological cover for a bombing campaign that killed hundreds of thousands of civilians through a combination of failed precision and deliberate area attacks. Production of Norden bombsights ceased immediately with the war's end. Factories that had manufactured tens of thousands of the complex devices sat idle. Skilled workers who had hand-assembled precision components moved to other employment. The massive industrial and financial investment in the Norden program, more than $1 billion, joined other wartime expenditures as part of the cost of victory. Carl L. Norden Incorporated was dissolved as a corporation on December 22, 1949, though Norden Laboratories continued as a research and development firm. Part 9. Legacy. The lessons endure. The story of the Norden bombsight did not end with the war's conclusion. The device saw continued use in post-war conflicts, though increasingly as a backup to radar-based systems. When North Korea invaded South Korea in June of 1950, B-29 bombers were pulled out of storage and pressed back into service. Their Norden Bombsights, many of which had sat unused for 5 years, required extensive maintenance to return to operational status. Retired World War II technicians were recalled to service because current personnel lacked training on the complex mechanical systems. During the Korean War, the Norden performed adequately in its limited role. The strategic situation differed fundamentally from World War II. United Nations forces enjoyed air superiority. North Korean and Chinese anti-aircraft defenses, while dangerous, were less sophisticated than German systems had been. Bombing missions targeted bridges, supply depots, and transportation networks rather than heavily defended industrial complexes. Under these conditions, the Norden's limitations were less apparent, though its accuracy still fell well short of what testing had promised decades earlier. The Vietnam War saw the last combat use of the Norden Bombsight. In 1967, the United States Navy's VO-67 squadron used Nordens to drop acoustic sensors onto the Ho Chi Minh Trail, the network of paths through Laos and Cambodia used to supply communist forces in South Vietnam. This mission represented a strange end for technology once touted as capable of hitting Pickle barrels from 20,000 feet, dropping sensors into jungle from relatively low altitude to detect truck traffic. By the late 1960s, precision-guided munitions using laser guidance and early electronic systems were entering service, finally achieving the accuracy that mechanical bomb sights had promised but never delivered. The development of smart weapons during the Vietnam War and their subsequent refinement through the 1970s and 80s represented the technological fulfillment of what the Norden had attempted. Laser-guided bombs could strike within feet of their aiming points, even from high altitude. Television-guided weapons could track moving targets. Eventually, GPS-guided munitions would enable precision attacks in any weather condition. These systems achieved accuracy through electronics and active guidance, rather than mechanical computation of ballistic trajectories. They represented fundamentally different approaches to the same problem the Norden had tried to solve. The lessons of the Norden program influenced military procurement for decades. The gap between laboratory performance and combat effectiveness became a recognized problem that defense planners attempted to address through more realistic testing. The tendency to build doctrine around technological capabilities that had not been validated in operational conditions faced greater skepticism. The psychological and moral implications of promoting weapons systems as precision devices, when their actual performance fell far short, received more attention, though similar problems would recur with subsequent technologies. Carl Norden died in Zurich, Switzerland, on June 14, 1965. He was 85 years old. His obituaries noted his invention of the famous bombsight, but said little about its actual combat performance. The mythology of Norden precision persisted in popular memory, even as military historians documented its failures. Theodore Barth had died 2 years earlier, in 1967, at his home in Cape Cod. His estate continued supporting charitable causes. Both men lived long enough to see their invention become obsolete, replaced by radar bombing systems and eventually by precision-guided weapons that achieved what mechanical bombsights could not. The Norden bombsights themselves became museum pieces or were scrapped as surplus. A few entered private collections. Museums across the United States displayed examples of the device that had once been among America's most closely guarded secrets. Visitors could examine the complex mechanism, the gyroscopes and gears and optical systems, and read plaques describing how bombardiers used these devices to achieve unprecedented accuracy. The plaques generally did not mention that combat accuracy fell short of promises by factors of 10 or more. The human cost of the Norden's failure cannot be precisely calculated. How many bomber crewmen died in raids that achieved far less than their promised precision suggested? How many civilians died in attacks that were supposed to be surgical strikes but became area bombardments? How much industrial and financial investment was diverted from other systems that might have proved more effective? These questions have no definitive answers, but they haunt the Norden story. The Fort Benning demonstration on April 19, 1941, where 10 of 12 bombs hit a simulated battleship target, represented the high point of Norden confidence. 5 days later, the acting chief of the Bureau of Aeronautics declared the bombsight America's principal factor of superiority. 4 years later, that confidence lay in ruins alongside the bombed cities of Germany and Japan. The technological promise had collided with the brutal realities of combat at high altitude over defended targets in extreme conditions. The ocean of confidence had proven less navigable than the engineers believed. The Norden Bombsight remains one of World War II's most famous devices, though perhaps for the wrong reasons. It stands as testament to American engineering capability and to the massive resources the nation could mobilize for weapons development. It also stands as warning about the limits of technology, about the gap between controlled testing and chaotic combat, about the danger of building strategy on untested assumptions. The engineers who designed the Norden created a mechanical marvel. What they could not create was a system that would maintain its precision under conditions that defied precise prediction. The ocean was never as controllable as the engineers believed. Reality asserted itself, as it always does, regardless of how sophisticated the technology or how confident the planners. The lesson endures, though whether future military planners will heed it remains uncertain. Technology promises precision. Combat delivers chaos. The gap between these realities defines much of military history. The Norden Bombsight, designed to hit 100-foot targets from 25,000 feet, achieved accuracy roughly equivalent to contemporary bombsights while costing far more and creating far greater expectations. The story of that gap between expectation and achievement remains relevant to modern weapons procurement and strategic planning. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.